Hello and welcome back to Differential Equations, section 5.4 on second order systems and mechanical applications. I am going to toss in electrical just, for the good measure, and we'll go from there. Now, these are second order systems, which means that if you are somehow able to turn this into the single equation, because we know we can do that sometimes, you would get the fourth order equation actually to solve. So we are going to use the eigenvalue method for this, and again, just the title that we are going into mechanical application, and then if I toss in the electrical, which we kind of skipped before when it was a single equation, you are expecting all of your answers to be oscillations, right? Full of sines and cosines, which means you are expecting complex eigenvalues every time, which is the long solution we studied the last time. Now, to explain these systems, we can take a system that has, three masses, for instance, and then go from there. You can have two masses, you can have 15 masses, whatever. The amount of masses will depend, right, on how many equations you have, but they are all of the second order because each one of them is that spring which has the position, right? You have the dampening possibly, and right, the mass of the object. So you have those three terms, but the mass times the second derivative is what tells you that it's a second derivative equation. So the amount of masses you have is equal to the amount of equations. So whether the system is going to have 3, 4, 5 equations, whatever, or 2, right? But they're all second order differential equations. So each one of them is second order, in contrast to what we had in the previous chapter 4, where all of the equations we had in our system were first order differential equations. So now, when you look at this, right, if I just draw two mass system, so mass 1 and the mass 2, and I connect them like this and put K1 and K2, right, for this particular system, we immediately know that the first one with the displacement, let's say x1, and the second one with the displacement x2, right, will depend on the way that they are connected. Now, I could, as I said, I'm not going to, but I could connect another spring over here with a K3 and then add an extra term. But just for the introductory problem, we don't have to do that one. So now, what are my equations? Well, they're exactly the same as what we studied in chapter 3. There is no difference, right? Because the free body diagram that you draw for each one of these, right? The mass 1 has impact from K1 and K2. So your M1 double prime, x1, sorry, double prime, because that's the displacement that you're measuring, for the first one is going to be negative K1 x1 plus K2 and then x2 minus x1. And that's it. Now the M2 x2 double prime is just going to be negative K2 x2 minus x1. So these are the same equations that we had back in like chapter 3, and then we now just have to put these into a system. Now, again, you get these K1 and K2 as numbers. So when you make the matrix, right, of these values, you can come up quickly with the, well, if you want to first look at this system as the matrix M times the X double prime, right, which is the vector, is equal to the matrix K times the x1 and x2. Now I can box this equation because, again, the equation here represents any dimension. So the amount of equations, which is the amount of masses that you have, will give us the amounts of all of these. So now we go and we say, well, if I look at my situation, what is my matrix M, right, for this case? Where my matrix M for this case would be M1, 0, 0, M2, right? So that will be the matrix. And X double prime would be simply X1 double prime, X2 double prime as a column vector. Now, matrix K is going to be matrix of coefficients, which is negative K1, and then we have, oh, I did not collect like terms, and I didn't do any of that stuff here. See that this is still the way it's set up. So I have to actually let's go here. So that's going to be M1 X1 double prime equals 2, and now X1's is going to be minus K1 minus K2 times X1, and then plus K2X2, and then M2, there we go. That's K2X1 plus minus K2X2. There we go. So my matrix for this one is minus K1 minus K2, and then just K2, and then K2, and then minus K2, right? So this would be my matrix for this, and then X is just X1 and X2, which are the solutions that we are looking for, right? X1 is going to be some solution in terms of sines and cosine, and X2 is going to be a solution in terms of sines and cosine because, as I said, both of these oscillate left and right, making these sines and cosines. That's it. So this is a 2x2 system, right? And we are able to now solve it using our basic ideas, where we can transform this into a system, right? And then just use, well, we can just use eigenvalue because we know that we can pre-multiply. So this is a little bit now of linear algebra, and if you didn't have linear algebra, I understand that you might have some extra questions. Leave some space here. We need K, X, like this. And now if I pre-multiply by M inverse, and we know how to find M inverse, right? We convert this system into X double prime, and then this M negative 1K is something that you can compute first, which will give you a new matrix, and then X like this, which ultimately looks like the system we always used to solve, right, of before, except it was the first order, right, and now it's the second order. And for this, we just go and pretty much solve everything the same way, where we have the eigenvalues, eigenvectors, and all of these kind of things. There is no difference in solving this system to what we did before, and we are still expecting to see, except this time we are guaranteed to see the solutions, right? So if this is a problem that we are trying to solve, then the solution will eventually, when you go through all of the hoops of calculation, will look like, let's do the same. So x of t, right, which is the vector, will look like the summation of all ai cosine omega I t plus bi sine omega I t, and times obviously the eigenvector. So now I goes from 1 to n, and n is the number of masses, right? So if you have 2 masses, then you are going to only have 2 of these. If you have, right, 10 masses, then you have 10. It is scalable, so so n is the number of m's, masses. So in our case, we only had 2 to begin with. I believe the book, let me see, book I think is using 3. Yes, book is using 3, and then they explain later on with, you know, whatever amount you want to have. It has to be final amount. Obviously, you can't have infinitely many masses because you can't compute for infinitely many masses. You can have 1,000,000 of them, but it has to be finite. So 1,000,000 is still, I mean, something that you will not be sitting computing by hand, obviously, but, well, you don't have a system of million of these masses connected anyway. But the thing is that, right, we don't care how many, because we can take care of any number of these using the same. And if you take a look at your solution, then you are going to have this look the same way as what you had for the complex values, right, from the last class. So solving the problem with values will just give you the matrix. So the question is, do you remember, do you know, right, the formula for the inverse of the matrix to come up with the inverse of the matrix? And again, to give something like this on like 3 by 3 for the exam, like you need like 10 hours to do it. Your exam is definitely going to have a 2 by 2 case, because that's what you can compute in some reasonable amount of time. Plus, we can't even bank on, 10 problems, given that, each problem is like 30 minutes. So very limited on what you can do. So we can take a look. Well, I didn't tell you about the special case because it's a repeated case, and we still haven't dealt with repeated cases, which is the next lecture. But if you have a system with 2 masses, right, where you have the spring like this, and let's say it's attached on both ends, right? So mass 1, mass 2, K1, K2, K3. And I'm doing this because I'm looking at the homework problems here. And let's say literally any one of these is fine. Problem number 4, for instance, tells you that the mass 1 is equal to mass 2 is equal to 1, let's say kilogram, and then K1 is equal to 1, and K2 is equal to 2, and K3 is equal to 1, right? So these are some things that, we immediately have. Now, you have your matrix, and M1 and M2 are both 1s, so we don't get to do the inverse because we don't have to worry about M's. I have to change the problem. Let's go problem 6, because problem 6 has different masses. So M1 is equal to 1, and M2 is equal to 2. K1 is 2. K2 and K3 are both 4. Okay, fine. There you go. I wanted this because I wanted different masses, so we can put everything in here. So the model, we have 2 masses, therefore 2 equations. It's 2 by 2 system. So we have M1 x double prime, right? This is the standard situation where we are setting up the problem, and you are looking into the same situation as before. So you have your setup, and then you have your calculation. So for your setup, you have negative K1 x1, right? And plus K2 x2 minus x1 for displacement. And as you can see, M1 is not connected to K3, right? So there is no K3 in the equation at all. Now, mass 2 is connected to K2 and K3. There will be no K1 at all for it. So M2x, oh, this is, I forgot to put in index 1 for the first one. So that's x1 and this is x2. All right, so this one, right, is negative K2 x2 minus x1 because it is, right, impacted by the oscillation of M1. And then we have minus K3 x2, which is the displacement, right? Because the first one has the displacement of x1. The second one has displacement of x2. And you can see how, right, the M2 on the left is impacted by the left mass, right, with the K2. And on its right, it's impacted by the fact that it's hooked up to the wall, right? Now, all I need to do is to simplify all of this, right? Plug in values and collect terms. So when I plug in M1 is equal to 1, I just get, I'm not going to write 1, I'm just going to say this, right? And then I have negative 2x1 plus 4x2 minus 4x1, and we'll collect the terms. Over here I have 2x2 double prime equals to, and I have now minus 4x2 plus 4x1 minus 4x2. This one is going to simplify, so I'm going to avoid the matrix again. Whatever. Sometimes you just have to give up. Okay. So negative 6x1 plus 4x2. And the second one is 2x2 double prime is equal to 4x1 minus 8x2. And now you see that when you divide by 2, you kind of lose that matrix in front that I wanted to do the inverse for and so on. Well, whatever. x2 double prime. You can't say I didn't try because I even switched the problem to avoid it, and that's what I get. All right. So here it is, right? And this is the system that we can solve, because now this system is clearly of the form, right? X double prime is equal to A matrix times X bar. In our case, X double prime matrix A is negative 6, 4, 2, negative 4, and then X bar. So I do have the matrix A, which I can go ahead and work out all of the eigenvalues and all of that stuff to come up with the solution. So now I'm not going to waste time solving this, because you should already know how to solve this from the previous lecture, right? You go your negative 6 minus lambda times negative 4 minus lambda minus 8 is equal to 0. Get your lambdas, get your vectors, right? So this gives lambdas, then you get your vectors, then you get your solution. There is no difference in solving. This is, again, application of the whole system, and it's for mechanical cases. Now, obviously, these problems become much longer and way more annoying when you are dealing with 3x3 system, 4x4 system, and so on, because, again, you have more lambdas to solve for. Now, also, note that your solutions are always sines and cosine, and they come from that lambda eigenvalue pair, which is complex, right? So that takes two solutions. So if you have two masses connected, your solution is always obviously complex, right? Because they oscillate. But when you have three masses, right, you are guaranteed one solution to be real, and the other two could be, right, complex, and they should be complex because the whole thing oscillates. Now, that real solution could be positive or negative lambda, in which case, right, the system will be picking up energy or losing energy, right? So you have to be careful with the 3x3 system and the computation of that extra, because as I said, right, 3x3 system, you have three lambdas, two of which are complex, which is the same calculation as this one, and the other one is that single real eigenvalue, which was the first problem we did in when we did eigenvalue problems. So three mass problems are technically the combinations of, right, they're combinations of the systems that we have. And now, if we are to, even though we said, mechanical applications, if we are to push the second order differential equations for electrical engineering, which is again the very basic for electrical, you have a circuit that has a source of some EMF, right? And then you can put whatever components you want, technically. So this will be your L1, this will be your L2, this will be your C, and this is R because I only have one. Maybe I can add another R over here, whatever, R2 and R1, right? So the issue with electrical is that you guys have to learn physics, and you have to learn the which is Kirchhoff Laws, which will be used and helpful for you to write the equations. See, because this over here would be, loop 1, and this over here would be loop 2, and then you can call this node A. And then you can set up some arbitrary currents. Remember that in alternating circuits, like this one is, the current is switching the polarity, right, back and forth, many times a second. That's what your hertz means, right? When you look at your chargers and things, say, 110, 60 hertz, right? Then you have your how many times the polarity switches per second, because hertz is 1/second. And that's printed on every single charger next to it, right? It has the input voltage, and then it says that the output is, let's say, 12 volts DC or 6 volts DC or whatever. Direct current has its plus and minus, which is why you can plug them in only one way. And the multi-dimensional connectors, like the ones you have, multi-dimensional, the connectors that you can plug in, like the USB-C that you can flip either way and plug in, because remember, the previous ones you can only fit one way, right? And that's why they are like those micro USB, right, things you can only plug in one way. But these guys that have multiple directions, right, they have multiple pins. So no matter which way you turn, always the pins align. And it's just, redundancy on their part to make the functionality so the connector can be flipped either way. Now, why is that important? Well, because I am going to draw direction for currents, I1, I2, and I3. And when I draw directions for currents like this, I immediately get this node here at A says that I1 is equal to I2 plus I3. And I get the node, that's the node value, and these are the currents in that node. Now, the rest of the currents in the circuit, we are going to deal with what we call voltage drops. Now, the voltage drops are calculated on each one of these components according to the formulas. I believe it was somewhere in chapter 3. I was trying to find real quick the page on which you had the voltage drops. If you remember, there was a voltage drop for capacitor, voltage drop for inductor, right? And they were all given in the for each one of these. I don't know where they are. I'm trying, but it's not working. Whatever. So anyway, for inductor, if you remember, I might have to. Oh, it was back in 3.7. Cool. There it is. Page 209. So those of you going into electrical engineering, guys, I mean, you have to know this, right? So for inductor, you have L di dt. For resistor is Ri. And for capacitor is 1 over C times Q, but Q was second derivative of I. And this is where you get your second derivatives. Now, this tells me that I have a terrible circuit up there because it's squared, right? Because my capacitor should be here, but that's okay. So it's shared by both loops. Whatever. So now, the sum of all voltage drops needs to be 0 in the loop, right? So when I add the 4 components that you see in the loop, their sum needs to be 0. Now, E is making electricity, and the other 3 are spending electricity. You can think about that way if that's easier, right? So it's going to be minus L1 di dt minus R1I and minus R2I, and everything equal to 0, right? And oh, I just realized we can't solve this because we didn't learn the forcing yet. Whatever. And then the second loop, right? The loop. So this is loop 1. And the second loop, loop 2, is going to have the second derivative, right? Because you have no sources here, so you can just pile them all up. So you have your 1 over C. Here's your second derivative of I. Oh, I have to deal with that as well. Okay, let's do loop 2 equation properly. So C2 with a capacitor, okay, so that's spending, and then L2 is spending, so it's going to be plus L2, so that's L2 di dt, and then I2 is the now the loop goes this way, and it's going opposite to the current, where before was going with the current, so now it's going to be a minus of R1 I3, and all of these guys are I2s. Because remember, we have 3 currents that are equal to 0. Now I have to go back to the first loop because I messed up. So E minus L1 I1, and that's good. And now I3 is, through R2 you still have I1 because I1 has to go through the entire branch. I3 is only on this branch. So that's R1I3 and then R2I1. Okay, good. So now when you take a look at these equations, this is why I said electrical engineering is much harder to use to explain these concepts, because you have to know so much more than, okay, here is a spring and it oscillates left and right, right? So you just have to know all of the Kirchhoff laws and nodal analysis and everything else in order for this to work, plus to assign which current goes through each branch, which is, guys, the same as understanding that the spring 1 has a K1 and the spring 2 has a K2, and each one of those springs is described by that particular spring constant. Well, you know, your first branch over here only has I1 going through it, so it's somewhat described by that I1. And then you have I2 I2 on the other side. So this is your I2 right here, right? And then all of this thing over here, and yeah. So what do I have? I have I1 is equal to I2 plus I3. That's one equation. And then now I have these equations here, and I have the first derivative. As you can see now, I have to push e to the other. Well, actually, if I do this, then this is equal to 0. There we go. And then I have I1, which has the derivative in it. So you have your negative L1 di1 dt minus R2 I1. So that's all I1. And then you have minus R1. Is it R1? Yeah. I3. I3 equals to negative E. So you can change all the signs to positive. Okay, cool. And from the loop 3 you have, and this is where your second order differential equation kicks in. So here's your d squared I2 dt squared, and then, oh, that's I2. Do I have I1? No, I don't have I1. Okay, good. That was lucky. di2 dt minus R1 I3 equals 0. Converting this system into the system of equations is much harder. But we can still do it. And what I have here is, oh, but we didn't still. We can't deal with these terms yet. There is a reason why this is at the end of chapter 5. We have a lot of holes that we have, but I'm hoping that you guys see that this equation here can be converted into 1 over c I2 double prime, you write it that way, plus L2 I2 prime minus R1 I3 equal to 0. Now, this would be somewhat equivalent to having an equation like A x double prime, right, plus, I don't know, B x prime, x2 prime, minus C x3 equals 0, right? So you see that it still depends on the solutions, right? X1, x2, x3. In our case, I1, I2, I3. It's just that, again, there's a reason why electrical engineering is 75% mathematics and 25% double E classes. Just to grind through this type of equations, especially later on when you take those double E courses that actually have this. Now, I remember taking these, working on these equations and solving them in my electrical circuits class when I took it, right, as a 200 level course. Now, I'm not sure if they still have it because the requirements for math are a little bit relaxed, right? But when I took circuits many moons ago, I had to have differential equations completed prior to taking circuits class. Now, if differential equations are either taken out as a prerequisite or they're put in even as co-requisite, then clearly you can't solve any of these equations because you still don't know them, right? And you don't know how to solve them. I mean, we still don't know how to solve this because we haven't had a second order system with the first derivative floating about. So if you take a look at your mechanical problem from before, there's no first derivative anywhere because there's no dampening in this case, right? And because there is no dampening in this case, there is no x prime. So the system was very easy to convert into the system that we can use like this. But our system cannot be written in this form in electrical that I have below, because the inductors made it sure, right, that we have a first degree system. So the first derivative around. If I am to kick out those two inductors and I just put capacitors and resistors, then we would not have this. And I should have done that, but now it's way too late. I just wanted to more of, again, it's not a part of the lecture. It is an extra that I'm adding in. So you can see the electrical engineering has the same stuff, except is way worse than mechanical. However, if I am to put a circuit together that only has capacitors and resistors without the battery, without the EMF, right, we can mimic the system. Because remember, if you just put a mechanical system like this, right, with two masses connected with springs, this system is not moving anywhere until you flick something, right? So you have to supply some kind of introductory energy in order for it to start oscillating and moving and going about. The same thing is with the electrical circuit, right? If I make a circuit with two loops, right, or with one loop or with 100 loops, it doesn't matter, right? And if I don't give it some initial energy to charge the capacitor, it's not gonna do anything, right? Now, capacitors store energy and they release it when you request the energy. So you can have the battery, right, like this, and then you can have a switch over here. Like this. So, and then you put the capacitor and you put the resistor in. So let's put the light bulb and the capacitor. So, no, wrong. Hold on. There we go. So when you flip down, it charges the capacitor. What the hell? I can't make a simple circuit. This is terrible. Okay, so one more time. I actually now set upright. So I want to switch the battery this way and charge the capacitor. So when I switch up, it charges the capacitor. When I switch down, there's going to be a light bulb or LED or something. There we go. So switch up, it charges the capacitor, and the capacitor will have charge in it. Now this is capacitor, where the two sides are the same. The battery has a longer side for the plus and shorter side for the minus. So when you flip the switch up, it charges the capacitor. Now capacitor has a charge, and then you switch the switch down, then this circuit is active and the other circuit is off, and now the capacitor gives its charge and lights up the bulb, right? So that's, you know, one way of thinking about it. So capacitors serve as storage devices, and your light bulb is technically a resistor, which is a spender, right? So I can't, you see that this circuit over here can work only when capacitor is charged, because if the capacitor is not charged, then it cannot power the light bulb. So I switch it up to charge the capacitor, then I switch it down to turn the light bulb on. And obviously that light bulb will quickly deplete the capacitor. So guys, think of the flash for cameras, right? That's exactly what is happening. It's high capacity capacitors store a lot of energy from batteries. You do not want to connect the flash light bulb directly to the battery, because the batteries cannot deploy so much energy so quickly. Batteries are very slow because they're chemical elements, and chemical processes take very long time, where capacitor is not chemical element. So capacitor stores everything in terms of charge, where battery stores charge as chemical energy and needs to be converted when requested. So the chemical composition of the battery changes when you are using the battery or when you are charging the battery if you have a rechargeable battery. Now, the chemical in a non-rechargeable batteries are different, so if you try to recharge them, they explode. I mean, they don't explode violently, but they do explode, and they have a little puff, and then they, get the chemical out of them. So the idea here is to understand that you can have a system without the battery working, but you actually have to charge that capacitor. So for your mechanical system, what I had to flick one of the two masses to get everything moving, that's the equivalent in my electrical circuit flipping the switch up to just charge the capacitor. And then when I flip the switch down, the circuit will work without the battery. Now, obviously, capacitors don't hold charge for too long. They are quickly depleted and so on, which is why the flash photography is just a flash, and then it has to recharge from batteries, flash and recharge from batteries, and so on. So now I could create a circuit that only has capacitors and light bulbs, which are resistors, right? The ones that are spending that energy. Well, converting that energy into light and heat, right? I'm not sure if you know that those conventional light bulbs, right, that we are phasing out are only 2% efficient. That's probably, yeah, it was a great invention of its time, right, with Edison and all that stuff. But it's, in terms of efficiency, probably the biggest garbage product we ever had. Now, again, revolutionary thing, we absolutely needed it, right? But right now cars are in that, like gas-powered cars are in that category, right? So when you have this light bulb, right, with the conventional, usually Wolfram coil, right, that you screw into the socket, right, it's 2% light and 98% heat, which you don't use these lamps, right, in your lamp to heat up the room. So you see that 98% of energy that you throw in the light bulb is actually wasted, which is why, any other type of light bulb is better than the conventional one, right? But again, to develop other types of lights, right, you had to have a conventional one first. But I want you to know, like, I don't really care where you stand on that argument of green and stuff like that and all of that, environment and all of that. That's something that I don't want to discuss here. I just want to say that, you are wasting 98% of your money when you are using these types of bulbs because only 2% is light. Okay, now that we understand this, if I am to create a new problem, I'm not going to spend any more time. We're just going to wrap it up here. But if I am to replace each one of these inductors with either capacitors or resistors, we would have a circuit that doesn't need this term. We would have to charge one of those capacitors first and let everything float about. We would create the system just like a mechanical one without the first derivative. Now, those of you interested in, obviously, electrical engineering people, you are invited to join office hours and ask these kind of questions. And maybe we can create a problem during the office hours, because this is important only for you, right? For electrical engineering. And again, it's not even the part of the lecture, but I wanted to toss it in. So this is it for 5.4. So you will be using the methods to set up the problem, what you learned in chapter 3. And then to solve the problem, you will be using the eigenvalue, which you learned in 5.2. So those are the two sections that are actually kind of pushed together to create this section of 5.4. So we're going to take a 5-minute break because I need that time for YouTube to refresh the whatever feed for my stream. It's anywhere between 1 and 5 minutes, so I can change the title. And then we are going to go with the 5.5, which is repeated roots for eigenvalues. If you remember, we did not have that case, and I was saying that that's the one we have to pay attention to. So see